All right, welcome back everybody. We are on notes number 24 and we're starting chapter 5 where we focus on polynomials. We'll be going beyond the book by the end of the chapter and doing some different things, but we're going to start in section 5.1 and look at exponent properties. And this should be a review for you. You should have learned all of these exponent properties in algebra, and you've probably been using them here and there in between. And we're also going to start looking at polynomial functions and do a calculator activity to explore the end behavior. So just like we saw in the last chapter when we looked at quadratic functions and expressions and equations, we'll be looking at polynomial functions and expressions and equations. Okay, so polynomials may have a lot of different exponents, so that's why we're going to stop and review our exponent properties. So suppose that a and b are real numbers and m and n are integers. So here's the product of powers property, and I'm not too worried about you knowing it by name. I usually would call it the product property, but you just need to know how to use it. So a to the m times a to the n is a to the m plus n. So for example, if you had 2 cubed times 2 to the 4th, that would be 2 to the 7th. You add the exponents. Power of a power property. A to the m power to the n power is equivalent to a to the m times n power. So for example, if you had 2 cubed to the 4th, that would be 2 cubed times 2 cubed times 2 cubed times 2 cubed, and that would give you 2 to the 12th. So the shortcut is to multiply those exponents. Power of a product property, a times b to the m power is equivalent to a to the m power times b to the m power. Okay, sometimes people make mistakes with this because they think that this is the distributive property, and sometimes people think that you can do this. A plus b to the m power is equal to a to the m power plus b to the m power, but that is not true. That is misuse of the distributive property. So an example for what you could do would be something like this. 2x quantity cubed is equal to 2 cubed times x cubed, and then we would simplify that, and that's 8x cubed. Next is the negative exponent property. So a negative exponent is really just a notation which means reciprocal. So a to the negative m power is equivalent to 1 over a to the m power. We can look at a pattern to understand this. So let's say we have 2 cubed, and that's 2 times 2 times 2, 8. Then we have 2 squared, and that's 2 times 2, 4. And then we have 2 to the 1st, and that's just a single 2. Notice what's happening every time we go down 1 power. We divide by 2. We have 1 fewer 2. So suppose we continue that pattern and we divide by 2 again. That's going to give us 2 to the 0 power equals 1. So that's a little bit of foreshadowing to our next property, actually, the 0 exponent property. A to the 0 power is 1, as long as a is not equal to 0. 0 to the 0 is another can of worms. Okay, what if we continue our pattern and we divide by 2 again? We would decrease the exponent again, so now we have 2 to the negative 1st power, and we have 1/2. So that's the same as 1 over 2 to the 1st power. What if we divide by 2 again? Now we have 2 to the negative 2nd power, and we get 1/4, and that's the same thing as 1 over 2 squared. So you can see how raising to a negative power is the same as 1 over that number to the positive power. It's the reciprocal. It also works if you have something like 1 over 2 to the negative 2 power. If you have a negative in the denominator, a negative exponent in the denominator, you can bring it up to the top and make it 2 squared. So a negative exponent in the numerator, move it to the denominator, and now it's a positive exponent. A negative exponent in the denominator, move it to the numerator, and now it's a positive exponent. The quotient of powers property, if you have a to the m power divided by a to the n power, that's the same as a to the m minus n power we could use what we had just done to understand that. So let's say you have a to the m divided by a to the n. Well, we've just learned that dividing by a to the n is the same thing as 1 over, I'll just rewrite it like this. Dividing by a to the n is the same thing as multiplying by a to the negative n. And then if we use our product of powers property and add those exponents together, we get a to the m plus negative n, so a to the m minus n. So once you have a few of these properties, you can develop the other ones from those. And then the power of a quotient is a over b to the m equals a to the m over b to the m. Okay, so an example of that might be something like x over 3 to the 4th power is the same thing as x to the 4th power over 3 to the 4th power. And then we could make that x to the 4th power over 81. So there we have all of our basic exponent properties. Let's work out some examples. So I have example 1 with 4 parts, and I think I have example 2 with 4 parts as well. So 1a is 4 squared to the 3rd power, so we have a power to a power, and we're going to multiply those, and that gives us 4 to the 6th power. Now, should you multiply it out further, I would say we don't have a hard and fast rule about this, but if it seems reasonable to do with a calculator and the number doesn't get humongous, go ahead and multiply it out. So this is 4,096. I would say use your property to first simplify and then use a calculator. If all you do is type 4 squared to the 3rd into your calculator and you don't think about the property, then you just might not have as much good working ability with that property. 1b, we have negative 8, which could be written as negative 8 to the 1st power times negative 8 to the 3rd power. So we have the same base in both. The base is negative 8. Add those exponents together and we get negative 8 to the 4th power. And since we're multiplying a negative by itself 4 times, we're going to end up with a positive. Negative 8 to the 4th power is 4,096. Another 4,096. Okay, so if we've seen it once and we've seen it twice, doesn't that mean we ought to conclude that every single problem is going to have an answer of 4,096? How's my logic there? You like it? Inductive reasoning, right? Okay, part C, we have 2/9 to the 3rd, so we can use the quotient of powers property, or whatever that was called, I don't remember exactly. Raise the numerator to the 3rd power and raise the denominator to the 3rd power. And then let's go ahead and simplify, and we get 8 over 729. Now part D is here because in this section you also have some problems that work with scientific notation. So if you remember scientific notation, you have a number of the form a times 10 to the b, let's say, where a has to be between 1 and 10. It can be, let's say 1 is less than or equal to a is less than 10. So you end up with just a single digit before the decimal point. And then b is the exponent. It's going to be an integer, positive or negative. So if you see 6 times 10 to the 4th, and even though there's a dot here, typically we would have a little times sign instead of a dot. 6 times 10 to the negative 4th means the same thing as 0.0006, moving the decimal 10 points to the left. And 9 times 10 to the 7th means the same thing as 9 with 7 zeros after it, moving the decimal 7 places to the right. Something like that. Okay, but in order to simplify the expression, I'm not going to change them out of scientific notation. I'm going to work with them in scientific notation. So 6/9, first of all, reduces to 2/3. And then we can use our exponent properties and subtract the exponents on 10. So we have 10 to the power of negative 4 minus 7. That would be 10 to the negative 11th power. Now, is this answer in scientific notation? Is our number right here between 1 and 10? It is not. So what we would need to do is multiply that by 10, borrowing that 10 from the other part of the problem. See, what I did was I multiplied that by 10 and I divided that by 10. Oops, divided by 10. Okay. We don't usually see fractions in scientific notation. It would be more typical to see a decimal. I just really don't like to have to round this, but 6, if I round it, it's 6.7 times 10 to the negative 12th. Okay, let's see what else we have. So these examples don't use numbers so much as they're using variables with the same exponent properties. So in 2a, we have a product. We have the same base for each factor. The base is x each time. So let's add these exponents together. Negative 6 plus 5 plus 3. Those add to 2. So we have x squared. And for b, we have two expressions being multiplied together. Remember, multiplication is commutative, so you can rearrange the order of what you're multiplying. So we have 7 times y squared times y to the negative 4th times z to the 5th times z to the negative 1st. I wouldn't expect you to rewrite it like that, but you can just think of it this way. So we have our 7, and then we're going to add the powers on y, and we get y to the negative 2nd power. And then we're going to add the powers on z, and we get z to the 4th power. Now here's the thing. If you're going to simplify, you're not supposed to leave a negative exponent in your answer. So then we can write this as 7z to the 4th over y squared, using that negative exponent property. Okay, part C, we have a quotient raised to a power, so let's raise the numerator to the power. And let's raise the denominator to the power. This is a step that you might just think instead of writing it out like I did. And then simplifying the numerator, we get v to the 6th power. And simplifying the denominator, we get t to the negative 8th power. But look, we have a negative exponent. And if it's in the bottom, then we can bring it up to the top to make it a positive exponent using our negative exponent rule. So v to the 6th power times t to the 8th power. Now, part D has a combination of lots of these properties, and it's possible that the order in which I choose to use them will be different from the order that you choose to do them. As long as we're doing it in an algebraically logical way, it should still work. So what if I choose to first simplify the x to the 4th over x cubed, and that gives me x, because you subtract the powers. And then I choose to simplify the y to the negative 2nd over y to the 6th, subtract the powers, and that gives us y to the negative 8th. And then I still need to raise that to the 3rd. So now I'll raise it to the 3rd, and I get x cubed y to the negative 24th. And because we have a negative exponent, we need to change this to x cubed over y to the 24th power. Okay, so that's a bit of practice with those exponent properties. The second topic is the end behavior of polynomials. So this really is unrelated to the first topic, but we need to squeeze two things in today. So this is what I want you to do. I want you to grab your book and your graphing calculator and do the graphing calculator activity on page 336. So I want you to pause the video and do that activity. When you're done, then you can resume the video, and what I'm going to do here on this slide is to summarize the results that you have found from the activity. So go ahead and pause. Okay, so we know that if we have the line f of x equals x is just a line with a slope of positive 1, so the end behavior is that as x approaches infinity, so as we're going out to the right, the y values, or the f of x values, approach infinity. They're going up. And as x approaches negative infinity, so that is the x values are going over to the left, the y values, f of x, approach negative infinity. So that's how we describe the end behavior. But if your line was y equals negative x, or the opposite of x, it would have the opposite end behavior. As x approaches infinity, f of x approaches negative infinity, and as x approaches negative infinity, f of x approaches infinity. Okay, I'm not going to take the time to write that out for each and every one of these examples on this page, but basically, if you see it going up, the y values are approaching infinity. If you see it going down, the y values are approaching negative infinity. So what you may have noticed when you looked at f of x equals x cubed was something like this, which has the same end behavior as f of x equals x. And then when you looked at f of x equals x to the fifth, it also may have looked something like this. And so all three of these have the same end behavior. Up to the right, down to the left. But then when you put a negative in front of them, remember our transformations, multiplying by a negative flips the thing across the x-axis, so you're getting the opposite end behavior. Left end up, right end down. So just like a line with a negative slope, a cubic or a quintic polynomial with a negative in front of the leading coefficient is going to have the same end behavior. Now we learned in the last chapter when we were studying parabolas that y equals x squared has both ends up. So as x approaches infinity, f of x approaches infinity. As x approaches negative infinity, f of x approaches infinity. It's going up on both sides. And we learned that if we multiply it by a negative, it's going to go down on both sides. As x approaches infinity, f of x approaches negative infinity. As x approaches negative infinity, f of x approaches negative infinity. And what you saw with the calculator activity was that f of x equals x to the fourth. It might be a little wider looking at the bottom, and same with x to the sixth. I'm just making rough sketches, but the end behavior is the same. So x squared, x to the fourth, x to the sixth, same end behavior. And then when you multiply it by negative x squared, negative x to the fourth, and negative x to the sixth all have the same end behavior. Both ends down instead of both ends up. So then you can generalize to other powers, like if it was x to the seventh, or x to the eighth, or x to the ninth, etc. The odd powers will have opposite end behavior, one end up, one end down. One end up, one end down, but if there's a negative in front of it, it's going to be reversed. And the even exponents, x squared, x to the fourth, x to the sixth, x to the eighth, etc., both ends up or both ends down. So that gives us a little piece of information that we're going to be able to use as we build on our knowledge of how to graph polynomials. Now, even if you had an equation like, or a function like this, f of x equals opposite of x to the fifth plus x to the fourth minus 3x cubed plus 2x minus 1. The only one that's going to influence the end behavior is the one with the highest exponent, because that exponent is going to drive what's going on in this polynomial function. So because it has an odd number here, it's going to have one end up and one end down. And because it has a negative here, it's going to be like a line with a negative slope, and do something like that. Or maybe it's more curvy. We're going to find out later. But the end behavior is what we're focused on right now. Okay, so here's your assignment. It doesn't relate to end behavior. That was just to kind of give us a feel for what was going on so we would be ready for tomorrow. This is practice with exponent properties. Thanks, everybody.